Hello, ladies, gents, and everyone's. It is Thursday, July 7th, and we're here to talk about this week's space and astronomy news. Okay, so last week we said that Rocket Lab successfully launched NASA's CAPSTONE CubeSat, which was at the time riding along on the Rocket Lab third stage. Well, boy, do we have some updates this week. That upper stage maneuvered CAPSTONE into place and released it onto its lunar ballistic transfer orbit on Saturday, leaving CAPSTONE under its own propulsion. And that all went fine, including its first 2 contacts with the Deep Space Network, until 11 hours later, nada. NASA revealed on Sunday that they were not able to communicate with the spacecraft, and the first of its planned trajectory maneuvers had to be delayed. Teams worked like crazy over the holiday weekend to figure out what went wrong and how, or even if, it could be fixed. Luckily, yesterday morning, contact was re-established with CAPSTONE. The spacecraft does seem to be in good health, although the root cause of the comms issue is still being investigated. Now that delayed first trajectory correction will be executed, and thanks to some flexibility in the plan, CAPSTONE will still be able to arrive at that strange near rectilinear halo orbit as planned in November. Hopefully this was a minor glitch that won't be repeated. It's definitely good to hear that CAPSTONE is operating and on its way successfully now. The ISS just said goodbye, adieu, sayonara, adios, auf Wiedersehen. I don't know. Anyway, to a cargo craft that has been riding along since February. The Cygnus spacecraft, a Northrop Grumman mission, launched to the station back in February, carrying with it over 8,000 pounds of supplies and scientific experiments. And last week, it was set free by the station's robotic arm, now carrying a much different cargo. Trash. The spacecraft and all the garbage it carried then entered the Earth's atmosphere and burned up somewhere over the Pacific Ocean. That's quite the garbage disposal. The next ISS resupply, CRS-25, is a SpaceX mission that is scheduled to launch sometime later this month. It was delayed from June due to a possible leak in the Cargo Dragon propulsion system. The logistics of keeping just 1,000 cubic meters of living space, which is about the size of a modest house, in orbit are not trivial. When we talk about black holes, we tend to talk a lot about their mass, for good reason. It's a fundamental property of a black hole. But black holes actually have 2 fundamental properties, the other being their spin. Of course, it's difficult to measure the spin of a black hole, but astronomers can do it by looking at X-ray emission from the accretion disk around a black hole. It can actually get closer to the black hole depending on the black hole's spin. And a team of astronomers announced last week that they made a spin measurement of the most massive black hole yet using NASA's Chandra X-ray Observatory. This black hole is a quasar with a mass of about 10 billion times the mass of the Sun. That's big even for supermassive black holes. The one at the center of our own galaxy, Sag A star, is only 4 million times the mass of the Sun. And what they found was that the black hole was actually spinning surprisingly slowly. About half the speed of a black hole the size of Sag A star. This actually points us to something about the formation of these supermassive black holes. See, the spin of a black hole actually increases if it's gaining mass via a kind of orderly accretion disk. But black holes that grow from merging of smaller black holes or from a kind of large unstable disk don't get this boost in spin. One of the lead astronomers on this discovery said, "The moderate spin for this ultramassive object may be a testament to the violent, chaotic history of the universe's biggest black holes." Damn, that's cool. You may know that due to tidal interactions between the 2 bodies, the moon is slowly moving away from the Earth, and the Earth's spin is actually slowly decreasing. And we can measure this lunar recession rate really accurately, thanks to lasers and mirrors placed on the moon by the Apollo astronauts. And actually, if you just rewound the current recession rate of the moon using basic tidal theory, you would find that it doesn't match the age of the moon. So the recession rate must have been slower in the past. But why? Various empirical models based on geological measurements of the Earth's history have been proposed over the years to kind of reconcile this and make it consistent. Empirical models, however, don't actually give us a lot of insight into what is physically actually happening, and some of these geological measurements from the Earth's ancient history aren't very accurate. This was the motivation for a team of scientists who this week proposed a physical model that was constrained only by the 2 data points we actually know the best, that is, that current lunar recession rate and the age of the moon. And even though they did not actually use that geological data to constrain the model, they found that their model actually fit some of that data anyway. So this is a pretty cool model, and for example, it possibly validates a technique called cyclostratigraphy. I'm probably pronouncing that wrong. which basically just uses rock layers to estimate the Earth's precession frequency in the past. As for the model itself, I'll spare you the details, there's a lot of math, but basically it comes down to the geometry of the oceans. So as the continents on the Earth drift and change shape, this changes what the oceans look like, which then changes that tidal interaction between the Earth and the Moon. And sometimes the shape of the ocean and those tidal interactions can interact in a way that's actually resonant, where basically you have these complementary frequencies that can cause an amplified effect. Crazy to think that the very slow movement of the continents over time has actually left an imprint on the orbit of the Moon. CERN's Large Hadron Collider is the most powerful particle collider in the world. It was used most famously back in 2012 to discover the Higgs boson, which was a long-predicted particle that can actually explain the mass of fundamental elementary particles. But the LHC has actually been off since 2018. The downtime was planned to allow for upgrades to the collider, but then it was also extended due to the COVID pandemic. But now, this week on Tuesday, the collider is back in operations. After the upgrades, the LHC can now reach collision energies of 13.6 trillion electron volts. During run 2, it could only do 13 trillion electron volts. The beams can now collide something like 28 quadrillion protons. It's a lot. This run is now planned to last for 4 years, during which scientists will be looking for things like more information about the Higgs boson, signs of physics beyond the standard model, and investigating previous anomalous collider results. Then in 2026, the collider will be turned off again for more upgrades. And of course, while physicists are obviously very excited about this, the standard model is also at the heart of what is happening in our universe. There is an entire subfield of astrophysics called astroparticle physics, or some field of physics called, it's both. For example, current theories about dark matter propose its existence as a particle, something that could potentially be investigated by a collider like the LHC. Indeed, previous LHC results have been used to narrow the range of properties that a potential dark matter candidate particle could possibly have. Congrats to the LHC team, and can't wait to see what they find. We are less than 5 days away from the first JWST results. And in case you aren't already excited enough about these images, which you should be, NASA gave us a little something to feast on this week. This image is from the JWST Fine Guidance Sensor. As the name suggests, the primary purpose of this instrument is actually to help the telescope find and lock onto targets. It uses imaging to help it do this, hence this beauty, but this is not scientific imaging. Which is insane because this is one of the deepest images ever taken, and it's a test image of the guidance system. JWST is that powerful. This image is unfiltered, and it's colored according to the brightness of the light received. Now, a few of these objects are stars, which you can tell because they have those pretty 6-pointed diffraction spikes. The rest are galaxies. Faint galaxies. Oh, and the actual intention of this test, which was to test its ability to lock onto a target and control the telescope's roll, was successful. And just produced this mind-bogglingly deep image of the universe as an, oh, by the way. Speaking of which, and somewhat unfortunate timing, I'm actually going to be at a conference when the images are released, so I won't be able to do a live stream, which some of you had asked about and I would have really liked to do. In fact, next week I won't be doing a news video either, but as soon as I can, I will try to make a video about these new web images for y'all, because it will be so good. Well, that's the space and astronomy news for this week. I hope you all enjoyed, and I will see you again in 2 weeks. Have a good one. Bye!